Welcome to our last session of this symposium. Today we have the honor to have here Professor Sciubba in order to continue his presentation of yesterday. Now he's going to talk to us about a fundamental reassessment of the Hess-Murray law based on force principles and on recent biological data. So please welcome Professor Sciubba.
Thank you. Thank you very much. Today you will understand why yesterday I insisted so much on topics like bifurcation, quasi flow, and entropy generation. We'll put all together in discussing this Hess-Murray law. The outline of the talk is the following. I will tell you first why I got into this research, and then I will give you the original formulation of a law, which is an allometric law. That's why we talked yesterday about allometric laws, which has been very popular in recent engineering and physics. Then I will give you a result. I will first analyze the law and then give you a summary of experimental results. I will maintain that the experimental results do not confirm this allometric law. And then I will take another route to derive a sort of different version of this law based on entropy generation rate minimization. Okay, next please. So the Hess-Murray law is an allometric law. We know from yesterday's lecture workshop what is an allometric law. Is a relationship between two different quantities, two different parameters in a structure. In this case, the Hess-Murray law links the radius of this daughter branch to the radius of the parent branch in a bifurcation. And the law was derived independently by Walter Rudolf Hess in 1917, and he was an Austrian, Swiss, and a Briton, Cecil Dunmore Murray, in 1926. The law says, on the basis of some considerations that we will develop later, that the radius of the smaller branch divided by the radius of the larger branch, the parent branch, is always equal to 1 over the cubic root of 2, which is something like a 0.79 something. The law was initially called the Murray law. It was Adrian Bejan in 96-97 who named it the Hess-Murray law. Okay, next please. The law, as we said, relates the radii of bifurcations. The law was subject to a lot of experimental and theoretical verification and validation, and the results are that the law is sufficiently accurate only for the smallest capillaries. It doesn't apply to aorta flow, which is turbulent, as you remember from yesterday, or to large veins flow, which is also turbulent, and it doesn't apply to a variety of real flows in which experimentally you see that the law doesn't apply. So the law would have been of interest only for the biologists or for some physicians if it had not been for Adrian Bejan, who is a very famous thermodynamicist. He is in Duke University in North Carolina. He assumed that the Hess-Murray law was always valid and took it as a basis for his constructal law. Some of you may have heard of the constructal law. Constructal law is a general law of physics, maintains Bejan, which he places at the level higher than the second law. So the fact that this law has been made popular again by constructal law pushed some people to investigate the basics, the fundamental assumptions behind the law, and the possible incoherences in the law. And that's what I'm doing today. I will show that both for natural engineering designs, a minimization of the reversibility, the entropy production, under realistic boundary condition leads to different results than the Hess-Murray law. And it's, I will also try to show that the Murray law, the Hess-Murray law, is only one of a number of possible laws that can apply to bifurcated flows. Of course, if the radii don't have the ratio dictated by the Hess-Murray law, then different structures can emerge, not built accordingly to the Hess-Murray law, but according to some other law, constant Reynolds, constant volume, whatever. And I will suggest at the end that we should go to an entropy generation based analysis, or exergy destruction. The entropy generation rate is equal to exergy destruction, as you probably know. But that is left for another lecture, so I will stop with the entropy generation minimization. Okay, so let's go to the history of this law. In 1906, I think, no, 1916, Hess, who was a physiologist, and he won the Nobel Prize in 1949 for his studies on blood circulation in the brain. In 1917, he approached the problem of determining the size of the capillary structures in the tissues of human and animals. And he wondered why these capillary flows happen to be so bifurcated. And he came up with a theory, which I will explain, which is based on an energy consideration, energy minimization, so to say, from which this 1 over the cubic root of 2 law comes out, 0.7937. This is a translation of the words of Hess. Hess wrote in German, of course. He says that there is an optimal ratio between the main branch and the secondary branch, and that is reached when, in situations in which you have to control the blood flow, the change in the area is such that the pressure drop in the main branch and in the secondary branches is the same. This is an energy formulation, because if you talk about the pressure drop for a given flow rate, you are talking about a pumping work. Pumping work comes from the heart. So this is an energy formulation, which was new for his time. Next, please. The way he derived this law is the following. First of all, he considered symmetrical branchings. Okay? This is the main branch, the first daughter branches, secondary daughter branches. He considered symmetric splitting, so that half of the flow rate flows on one side, half on the other side. And he said, the pressure drop in each one of these branches is given by the Poiseuille law, which we saw yesterday. But the pressure drop multiplied by the the flow rate gives you the pumping work. Okay? So the work which is lost by friction in the branch. He calculated then the total work expenditure, which is the sum of the work given by the pumping work, so the work that you have to used to overcome the friction, and of the volume of the blood which is in the system, because he assumed that there is a cost for the body to generate the blood and to maintain the blood. Okay? So if you have a very large branch with a lot of blood inside, the pressure drop is very low. So the frictional losses are low, the pumping work is low, but you have a lot of blood. So the body has to maintain and pump a large flow rate of blood. If you have a small capillary, the flow has a lot of friction, but there is a little blood flowing through it. So there must be a balance in between. What he said is, suppose there is a stress situation. You know that the body controls the blood flow by squeezing or enlarging the capillaries, the diameters. And he said, let's take an energy criterion. The variation of the area is such that it maintains always the same ratio relative to the pressure drop. In other words, the pressure drop under stress situation, when the veins contract or enlarge, remains the same in the main and in the secondary branch, pressure drop. To do this, what he did, he used the Poiseuille flow. This is the resistance, which I called W yesterday. Delta P divided by the flow rate is 8 mu viscosity times L divided by the area squared. And then he said, if I derive with respect to the area this resistance for the main branch and for the smaller branch, these two must be the same. So the variation of the resistance with respect to the area, which is with respect to the radius, must maintain the same value. You do this, you substitute this for the area ratio, and you get this formula, 1 over the cubic root of 2. What is new about, next please, what is new about Hess' formulation is that he was the first one to try to interpret the blood circulation in an energy way, and keeping in mind the goal of the transportation of blood, the teleology. He has a teleology of blood transportation, circulation, which nobody before him had shown. This is the original picture from his paper showing what he meant as bifurcation. Okay, all symmetrical bifurcations. This is not a real human tissue. It's just his drawing of illustrating what he meant in his calculations. Okay. Again, he also wrote, the bifurcation splits the flow, but the supply requested by the organs, which are here, is determined by the metabolic rate of the organism. So there is a certain Q, flow rate of blood, that has to be delivered. But the bifurcation does so with the minimum possible flow volume of blood. Okay? This is a sort of a contradiction we will see later, but this is the formulation of his law. Next, please. Hess' law was revisited and re-derived by Murray in 1926. Murray says in his papers that he's offering a new derivation, and that his formulae cannot be derived from Hess' formulation. This is not true. Hess' formulation can be extended and expanded to get the same results as Murray, almost all of the results. Murray was concerned with the transport of oxygen into the cells. And he wanted to identify the most efficient means of transporting this oxygen to the cells. Of course, the oxygen is transported by the blood circulation. So he tackled the problem in a very similar way as Hess did. he said, if we have capillaries that are too small, then the pressure drop is too high. If the capillaries are too large, the pressure drop is small, but you have a lot of blood circulating through the system. So you have a lot of pumping work, which is called cost of blood. Okay? Because if you have more blood, then your heart has to pump more hard, and you need a higher metabolic rate. You need to eat more. You need to eat more to supply yourself with energy sufficient to pump the blood. So he said there must be a compromise between the two, and he derived the cubic root of 2 rule. The next, please. Next slide. He did that. First of all, he writes what he calls an energy balance, which is really a power balance. It's in watts. This is the total power consumption for the circulation of blood in a pipe of length L and radius R. This is the pumping work. It's Q delta P. You remember yesterday we mentioned that Q delta P is actually a power. Okay? Is the pumping power that you need to circulate that blood against the pressure drops. And what is this? CB is the cost of blood. He calls it the cost of blood. And this is the volume of the blood in the capillary. Okay? So then he says, I derive from here the cost of blood assuming a certain metabolic rate. Okay? Because he knows how many watts or calories per day we use, and he derives the cost of blood. Then, with the cost of blood, he takes the derivative of this equation, which is the delta P, for each one of the bifurcations. That is the derivative of the delta P here plus the derivative of delta P in the secondary branch, and he obtains another time the cubic root of 2 result. There is one thing here. He repeats the calculation of the specific cost of blood several times. And of course, as you can see from here, the calculation depends on the size and on the delta P. This is a weakness of his result. And as a matter of fact, he repeats the calculation for 3 times, and he gets the 3 different values for the cost of blood. But he says this cost of blood is relatively constant, not too much different. These values are not too much different. So he maintains that his method is correct. But this is something that you have to keep in mind. Okay, so both Hess and Murray derived this ratio of 1 over the cubic root of 2. Next, please. If the law is correct, then as a consequence, the pressure gradient in the branch, in the daughter branch, divided by the pressure gradient in the main branch is equal to the cubic root of 2. Cubic root of 2 is 1.26. So that formula says that if the Hess-Murray law is true, then the pressure gradient increases in the smaller capillaries, which is confirmed by experimental values. It also says that under the same stipulation, the velocity decreases 1 over the cubic root of 2, which means 1 over the cubic root of 2 is 0.7937, something like that. So the velocity decreases about 20% in each bifurcation, which also seems verified by experiments. If this is true, the Reynolds number also decreases with the branchings because, of course, it scales with the delta square. These are all allometric laws. Okay? Remember what I told you yesterday? Allometric laws must be verified, validated by experiments. So these are 3 consequences of the Hess-Murray law. Next, please. Now, a novelty of Murray's formulation is that he was able to compute the angle of the branching. Next, please. He reasoned, this is an original drawing in Murray's paper. He reasoned, very interesting reasoning. He said, suppose that this is the optimal bifurcation. Okay? I don't know which one it is, but it is the optimal one. The optimal one has two angles between the bisectories of this line and the two branches. Okay? Now, if I can find another geometry, which is another two angles, which lead to a lower work, then that is not the optimal configuration. But if I cannot find such new values for the angles, then that is the optimal configuration. So he uses an approach which is similar to the virtual work approach, which you do when you compute in variational calculus, for instance, the optimal path. So he takes another path, computes the angles, and shows that the work is really the least when this configuration is attained. In other words, he shows that whatever change in the angles, you have a positive and additional pumping work. By doing this, he derives two values for cosine alpha 1 and alpha 2 as a function of the radii. For symmetric bifurcations, this is the formula that you derive from his work, which means since you can substitute here the value 1 over cubic root of 3, cubic root of 2, you get an angle alpha 1, alpha 2 for symmetrical bifurcations, which is 37.5. So that means that if the Hales-Murray law holds, any bifurcation should have 75 degrees angle of bifurcation. 37 on one side, 37 on the other side. Next, please. No, please. I forgot to mention that in this formula, the L, the length of the branches, does not appear. So in Murray's formulation, the length is not related to the radius in his optimal branching. Okay? He doesn't consider the ratio radius divided by length, which is called by Bejan, will be called by Bejan later, the slenderness ratio. Okay? Next, please. Thank you. In 1997, Eddy and Bejan, who is a thermodynamicist, rediscovered the Hess-Murray law and formulated a theory in this way. Assume as an assumption, as an hypothesis, fundamental hypothesis, that the Hess-Murray law applies. Okay? I'm not going to discuss it, whether it's good or not, it applies. Then every structure must have the radius ratio 1 over the cubic root of 2 and the splitting angle given by Murray's law. Okay? So we can construct, that's why constructal theory, we can build, design structures or interpret the natural structures by using this law. And we don't need to worry about entropy generation anymore, or efficiency, second law efficiency or whatever, because we know that since the Hess-Murray law says that if the radius ratio is 1 over cubic root of 2, the structure is optimal, any structure which is built under the Hess-Murray law is optimal. So any transport, okay? You can transport blood, sap in plants, water, electricity, energy, thermal energy, people, sand, whatever. Okay? He applied this law to several cases of transportation from one point to the other, and always applying this cubic rule of 2 rule. There is a lot of merit in this theory, which I don't like. Okay? My talk today is against this theory. But you have to acknowledge that it has merits. Okay? I will tell you what I don't like. I don't like that he assumes that the Hess-Murray law applies. Okay? This is not second law of thermodynamics. He says that the constructal law is above the second law of thermodynamics. And in fact it is, because if the bifurcation goes this way, then entropization is realized. Okay? Doesn't say the other way around. Doesn't say if entropy generation is minimized, then you get a certain delta ratio. Okay? Goes the other way. This is the weakness that I don't like. But it has a lot of merit in which he expresses very nicely, nature is not fractal. Why? Because you know that there have been mathematicians who have tried to claim that the natural phenomena can be expressed in mathematical forms which are given by fractals, Lyapunov exponents. I'm sure you have heard about these things. Turbulence was interpreted as a fractal phenomenon. The snowflakes are fractal, some people say. The Bénard convection cells, when you boil oil on a narrow strip, just a little level of oil, you see the emergence of hexagonal cells. They boil and go like that. They are fractals, and so on and so on. Bejan says, no, they are not fractals. They are constructals. And that's a great merit. Nature doesn't know mathematics. Nature doesn't know Fibonacci's triangle, the golden section, or whatever, some irrational number. Okay? Nature works according to physical principles. And Bejan contends, being not fractal, follows another law, which is constructal law. Okay? So this is a big merit of his law. Now, of course, he says that the goals dictate the evolution of the structure. Like a bifurcation doesn't exist from the beginning. There is a branch, and then at a certain point it bifurcates. Why does it bifurcate? Because it has to take blood in 2 different points. That's what Bejan says. Okay? That's a teleological interpretation, again, of nature, which is, I think, very correct. Okay? There is no natural branching. There is no God that says, be the branching. No. Some structure is a river. A river flows, and then at a certain point branches. Why? Because there was something in its bed that forced him to split. Okay? And then when it splits according to certain laws. Bejan says constructal law. He applies this law also to the delta of rivers and to the branching of trees and so on. Okay, so it's a more physical interpretation of the Hess-Murray law. Next, please. Bejan findings are very much engineering-like. Okay? In fact, he designs, or he offers procedures to design heat exchangers using his constructal theory. And this is, I think, the nicest definition I could find in his papers and books of constructal theory. You can read it yourself. The text of this presentation is on the computer, so you can copy it, download it the way you want. The most important thing is that he says in the geometry, which is constructal, the pressure gradients are higher in the smaller vessels. And this is completely in agreement with the Hess-Murray law. Okay? So the theory is coherent. Okay? There is no slip in the theory. Next, please. Well, let's see. Allometric law. Let's validate it. Okay? First of all, there were some people who started saying, well, the vessels, the capillaries, have a thickness. So there is an external radius you should take care of, not the internal radius only. when you compute the pressure? Well, this can be answered very quickly. Yes, but the thickness of the capillaries is 1 cell. 1 cell means few microns. Okay? So radius, internal radius of external radius is the same. Another objection was, yes, but the branchings might be three-dimensional. So you have a branch which goes like this, and then it branches this way. There were studies that showed that 90% of the real branchings are complanar. They are really two-dimensional, in the sense the first branching goes like this. If this branch splits like this, it splits in another plane, but it's still a 2D splitting. Okay? So the first split is like this, the second split is like this. But this and these two are still in the same plane. Okay? So there is no case for the three-dimensional branchings. Fractals were tried, but the agreement was not great with experiments. But the big drawback is that experimental findings do not confirm the Hess-Murray findings, the Hess-Murray predictions. First of all, the delta is only valid for laminar flow. This is the 1 over the square root of the cubic root of 2. For turbulent flow, the value should be 0.74. For arterial flow, 0.77. These are not big differences, but already tell you that something is wrong in the formulation. But moreover, much more important, the pressure gradients in successive branchings, they do not scale only with radius. Experimentally, you find out that they scale also with length, which is, by the way, is rather intuitive. Okay? So the Murray law, Hess-Murray law, predicts a delta P function of R only, of delta. Experimental findings suggest that the delta P depends, with another allometric law, from L over R, or R over L, the slenderness ratio. Okay? And this is the most serious contradiction of the Reynolds, of the Hess-Murray formulation. Next, please. There is an advantage. No formulation of the, nothing in the formulation of the Hess-Murray law says that it applies only to blood. So that's an advantage. You can apply to pipelines, to hair, to blood flow, sap flow, any other type of conduit. As long as you keep the law, the formulation of the cubic root of 2. And there is, this is also an advantage of the law. If the law holds, then you could explain somehow, the growth of structures. Why? Because suppose there is a plant which has one single stem. Then at a certain point the plant splits like this. Okay? Well, and then each branch splits again. Why do they split? They split teleologically because they need more leaves to catch more sun. But applying the Hess-Murray law, if the law applies, if the law is valid, you can apply the law to tell how thin the vessels are and how long they are, and what is the angle in between. So you can predict the development of a tree, for instance, or a plant, or of a tissue. And finally, you can use the Hess-Murray law to scale allometrically between different beings. An elephant has a much larger heart than I have. But if the Hess-Murray law applies for the elephant as well, then the ratio delta R1 over R0 for the elephant is the same as my R1 over R0. His R0 is larger, okay? But the scaling is the same. And that allows you would allow you to make an experiment or a finding on some animal and project the results towards other species. That's a very important fact. Next, please. Well, in spite of these successes, what we can say, generally speaking, is that the law is fascinatingly interesting because it derives a structure from an energy balance, power balance. Okay, but the allometric law doesn't seem to hold for the slenderness ratio, as we saw, and the experimental evidence shows that delta ranges from 0.4 to 0.85, which is okay. 0.79 is in between, but why do we have different deltas than 0.79? Okay, we have a whole range of deltas from 0.4 to 0.85, and in some cases we have 1 as a ratio of the bifurcation. Okay, so we need to find something else. Next, please. We saw that yesterday, entropy generation. Why am I interested in entropy generation? Because the entropy generation multiplied by T0 gives you what is called the Guisto-Dola lost work. It's the work lost in irreversibilities. So it's a work lost in inefficiencies of the system. Now, if you look here, this is what I was, remember yesterday I told you there is a phi function, capital phi, the dissipation function. This is a dissipation function in 2 dimensions for a cylindrical coordinate with circumferential periodicity. dV over dr, r is the radius, v square over r, du over dx, x is the axial direction, plus du dr plus dv over dx squared. All the terms are squared. So the function cannot be negative. The function, dissipation function, can only be positive or 0. If it's 0, all of these things are 0 because they don't algebraically add to each other. They're all positive. So this is the dissipation function. And multiplied by nu and divided by T gives you the viscous entropy generation rate in watts per kilogram. I think it's wrong. It's watts per Kelvin. Yeah. This is wrong. There is no kilogram here. And this is the thermal entropy dissipation, which is given by, remember yesterday there was a formula, nabla T squared divided by T squared. This is the gradient of the temperature squared. All of these terms are positive and divided by T squared. K is the conductivity of the fluid. We will only consider isothermal flows, so there is no thermal entropy generation. So we will use this. Next, please. Well, if we approach a way to criticize a theory is to approach it from scratch. Okay? You draw a bifurcation and then start thinking what happens here. Well, let's think the way Bejan does. Bejan says, the Hess-Murray law tells me how to bring some blood from point O, the source, to 2 points A and B, the sinks, or the users. Okay? Now, let's admit that this is the function of the bifurcation. We will see there is a slight modification to this theory or idea. But then, if the 2 points A and B are closer or farther away from each other, the area which is served by the bifurcation has an influence on the shape of the bifurcation. Because if point A is here and point B is down here, then the bifurcation looks very different from what is drawn here on the blackboard, on the wall, actually. Okay? Well, the same applies for triangular shapes, as Hess assumed. Well, the strange thing is that by using elementary trigonometry, you can relate L1 and L0 to alpha 1, the half angle of bifurcation, which I call the angle of splitting, and to A, which is the aspect ratio of the domain. This is not an allometric law. This is a trigonometric law. So this is absolute. This is always valid. Doesn't depend on the delta ratio or on blood or sap or anything. This is mathematical law. And so we have that lambda 0, which is L0 over L, is given by this value, 1 minus A over 2 tangent alpha 1, and lambda 1 is given by A over 2 sine alpha 1. So this tells you that there is a relationship between the shape of the domain of interest, the angle of splitting, and the length of the branches. It tells us also another thing. If you go and look at the triangular shape, obviously alpha 0, if alpha 0 is this angle and alpha 1 is this angle, alpha 1 is always larger than alpha 0. Alpha 1 becomes equal to alpha 0 when L0 gets to 0 and there are only two L1 branches. So it's a limiting case. This tells you that for triangular shape, the Murray cosine law, which I showed you before, does not apply. So if you try, because it leads to negative deltas. Okay? So Murray's law, the relationship between the angle and the delta, which I showed you before, does not apply for triangular sections. So this is another weakness of the formulation, because if formulation is valid, it should apply to any shape. Next, please. So let's make some assumptions. Steady flow, laminar flow, the fluid is Newtonian, and it's isothermal. And we assume the validity of these trigonometric laws which we just derived. Okay? Next, please. You don't have any questions? Sleepy today, huh? Okay. So, I want to approach the balance from a different point of view now. I told you, you have to go back one slide, that I would agree with Bejan that you have an origin for the blood and 2 points of delivery. Now, I change that attitude a little bit and start thinking a different way. What is the reason of the capillary network? To deliver blood. Only to point A and B? For surely not. The capillaries, as we saw yesterday, are permeable. The walls are permeable. So the flesh, the structure which is around the capillary gets oxygen and whatever, vitamins, all the nutrients through the wall of the capillary. So it's all of this area that is served by the flow which comes through the wall of the capillary. All of this area, not only points A and B. Okay? What may happen in points A and B, either they split again to serve another area, or they join again to absorb the detritus, as we mentioned yesterday, from the surrounding tissue and bring it back to the veins. So it's not a point-to-point transportation. It's a point-to-area or to volume flow. The blood goes from O all over the area, the white area of the domain. Okay? And then the domain is maintained by this blood flow. But then, next. Let's see, what is the phenomenon? Blood is pumped through the heart, by the heart, goes through these vessels, and there is a pressure loss. The pressure loss multiplied by the flow rate leads to an entropy generation rate, which is an irreversibility. what is the most efficient tissue? The tissue that delivers the highest flow rate with the minimum delta S. Okay? Minimum irreversibility per liter or kilogram of blood delivered to the body. Okay? Nobody can object to that. If I have a body and I have to deliver so and so much blood because of my metabolic rate, then I deliver that body with 0 losses or 0.1 losses or 1 losses, 1 joules per kilogram, whatever. That does make a difference. I'm less efficient the higher the delta S. The higher the delta S divided by MD. MD is, next please. No, I skipped next again. Oh God, I skipped a lot of, next. 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 Again. MD, sorry. MD is the mass that is delivered through this capillary. And MD is proportional to pi r to the surface of the capillary, L. So it's pi r0 L0 plus twice pi r1 L1. Okay? Now you can go back 5 times. So, next, up. Yeah, okay. Yeah. So, this is my final goal. I want to get to a point in which I have a parameter which is delta S over M as my optimization parameter. But before doing that, I want to show you one of the premises which I made at the beginning, and I told you the Hess-Murray law is only one of the possible laws. Okay? Let's discuss why. If we look at the entropy generation, we said yesterday that the entropy generation can be rate in watts per degree, this is correct, can be calculated by multiplying the delta P times the mass flow rate, the volume flow rate, delta P times Q. Okay, if you do that, you obtain this formula. Okay? S0 is the loss, the irreversible loss that you get in a pipe of length L0 and of radius R0 when the temperature is T0 and the viscosity is nu. Next, please. And that is a formula that you can compute. This is the main branch, unsplit. One bifurcation. You have to add this to this, and you get this. So this is the total entropy generation in a branching. As you see, this can only be positive. So a branching always includes implies a higher entropy generation rate. So there must be a reason for nature to branch, because nature doesn't like wasting energy. Okay? So if it branches, it must be an advantage, because the entropy generation is going up. And if you have 2 branches, then you get this formula, 3 branches, n branches. But these are all formulas which can be computed in a closed form. Okay? S0 being a reference is convenient to use a dimensionless or normalized entropy generation. So if you divide all of these by an S0, which is this, so you can compute it anyhow at the beginning, then you get 1 plus lambda over 2 delta 1 square, and so on and so on. All dimensionless quantities that are very convenient to be examined or compared to each other. Okay? Next, please. Well, since I have these formulas for the entropy generation rate, and I don't believe that the Hess-Murray law is the only law that applies, I start making assumptions. The branchings take place keeping the velocity the same before and after the splitting. That's an assumption. Okay? I like that. Second assumption. The branching maintain the Reynolds number before and after the splitting. the branching are such that the volume of the pipes is the same. So the sum of the volume of the two branches is equal to the volume of the main branch. And so on. I could create as many assumptions as I want. I use these assumptions to calculate delta. If the velocity remains the same, remember that the flow rate splits equally across these branchings, then delta is equal to 1 over square root of 2, not cubic root of 2. If the Reynolds number is constant, then delta is equal to 1/2. If the volume remains the same, then delta is related to lambda, and so on. Of course, Murray's law, delta is equal to 1 over the cubic root of 2. I listed 4 assumptions. One is Murray's law, and other 3 assumptions that I invented. But constant Reynolds number is something we do like in fluid dynamics, for instance. Constant velocity too. Constant volume we like in structural mechanics. Okay? So these are 4 assumptions which are logical, plausible, let's say. Okay? You cannot say a priori, no, I don't like this. And as a matter of fact, there is no reason a priori for which each one of these must happen in nature. A tree doesn't know the Reynolds number, doesn't know the velocity as a concept, doesn't know Murray's law. A tree bifurcates because of some other reason. Okay? So it might bifurcate according to any of these laws. So which one is the most likely in an evolutionary sense? The one which generates the least irreversibility. Because over millions of years, if a plant has a higher irreversibility rate to maintain the same circulation of sap, it will become extinct. Because another plant which is more efficient will get the same energy with less expenditure and generate more seeds or more leaves or become bigger. Is this clear? Okay. So let's see the results next. These are the results. Remember that the alpha angle and the length L1 and L0 depend on the aspect ratio. So I plot the results for 3 aspect ratios. H over L, these are rectangular shapes. H over L equal 0.2, 0.5, 0.75. Now what happens? This is the normalized version of the entropy generation rate. And this is the angle alpha. Okay? Now, for slimmer domains, the constructal theory is the best, that is the least irreversible, beyond 15 degrees of splitting angle. Okay? For wider domains, 0.5, they are wide, half as they are tall. The constructal becomes the best one after about 45, 50 degrees of splitting angle. And for flat domains or fat domains, larger domains with respect to the height, the constant volume is constantly a better solution than the constructal theory. The Reynolds number, constant Reynolds number, is always has always a very much higher dissipation rate, entropy generation rate. So it has to be discarded. In nature, it's likely that there is no constant Reynolds bifurcation. I didn't plot here the velocity, constant velocity, because experiments show that in the bifurcations, the velocity goes down with the bifurcation size. So the flow slows down when the radius becomes smaller. So that's experimentally discarded already. But this solution tells you, there are at least 2 laws that are competing in this kind of geometry. Okay? Constant volume, constructal, or Hess-Murray. So Hess-Murray is not the only legitimate law which assures you the minimum entropy generation rate. Okay? Next, please. And in this slide, I made a criticism. I will skip over it. I tell you practically why I don't believe in the Hess-Murray law. These are technicalities. Next. And we get to the idea which leads to the final solution. The capillaries are permeable. I showed you yesterday. What is the function of the capillaries? Well, blood comes through the arteries, bringing some nutrients to the tissues. Then the mass is ejected through the walls of the capillaries and goes to the cells. But then in the second half of this network, the detritus from the cells gets into the capillary wall and is carried through the veins again to the heart to be pumped. So the capillaries have a double effect. They supply nutrients and drain, let's say, waste. Okay? Now, this already gives the idea of a network instead of a bifurcated dendritic structure. And if you look at, this is a real enlargement, microscopic enlargement of a capillary network. I mean, these don't look like bifurcations. This is a sort of a polygon. This is a pentagon, as a matter of fact, and so on and so on. So this is a network and reinforces our idea that the general feature of this thing is to supply through diffusion some nutrients and to drain by diffusion some other nutrients. And so we go back to the idea, next please, which I discussed before, that the minimum irreversibility for the same mass flow rate of sap or blood supplied. These structures are everywhere. This is the enlargement of a tissue of fat in a mouse. This is obviously a leaf. This is a leaf, and you can't see it here, but it's very clear in the PPT, in the PowerPoint, that these are not bifurcations, but there are small lines that go through the bifurcations. It's a network. It's not a dendritic structure. And this is a three-dimensional rendering, experimental, of the capillary network in the brain. Okay? I don't see bifurcations here. I see a network. Okay? So that reinforces my idea that I have to treat this thing as a network. Next, please. So I go back to the slide which I showed before. This is one bifurcation now, one bifurcation symmetrical. SL is the same as S0. It's a reference entropy generation rate. One bifurcation, this is the entropy generation. This is the mass which is delivered. So I also make that, normalize that with respect to the mass through an L0, which would be the mass that would be supplied if there was only one branch without splitting of length L, not L0. And I divide this by this, and I say that the most efficient configuration is the one for which this ratio is the lowest. Okay? Minimum irreversibility per kilogram of blood supplied. Okay? Let's see at the results. Next. To do that, I have to define the area of influence. That's a weakness of the theory, actually, now. We need some more experiments to see. What I have to assume that this branch, the main branch, delivers blood to all of this rectangle, and that the smaller branches deliver blood to this rectangle. But this is a very crude assumption. It's likely that there are different shapes for the areas which are supplied of blood by this thing. So the results may change numerically, but the idea is the same. Now, what happens if I assume these areas, A1 and A0, as the influence areas of the single branches? Next, please. I get this result. this is the aspect ratio. Very slim domain, fatter and fatter domains, until here I have 1. So a domain which is square. The alpha 1, the optimal angle, semi-angle of splitting, increases from 27 to 34. Okay? The delta, the ratio of the radius, which should be 0.7937 according to the S-Murray law, varies from 0.445 to 0.414 and depends on the geometry of the domain, which I like. Lambda 0 and lambda 1 also depend on the geometry of the domain, and the ratio, the sigma, the entropy divided by the mass flow rate delivered, is different for different domains, and it's higher for square domains than for slender domains. And these are the results. Now, qualitatively, I like these results. Quantitatively, I cannot tell. Well, if this was true, then any network that I examine should be near this area, because the entropy generation per delivered blood is the smallest. Okay? And this is subject to some numerical and experimental testing. We have to run some experiments, and numerical and physical laboratory experiments, to see if this applies or not. But this is the result of the theory. Okay, next please. This is just what I just said. Go ahead. Go ahead. Now, the conclusions. Hess-Murray law is not the law which rules blood supply or sap supply in bifurcations. There are many other laws, actually an infinite number of laws which you can generate, and it's not necessary that the Hess-Murray law gives you the lowest entropy generation rate. But if you, instead of having the energy balance, power balance of the Hess-Murray law, you have a diffusion balance, a mass transport balance for the blood in the bifurcation, then you get a different formulation, different results, which seem to justify some of the experimental findings. The deltas here vary between 0.45 and 0.4, and experimentally between 0.4 and 0.85. So there is range for adjusting the theory, okay? Probably through the introduction of some diffusion coefficient, okay? So this is my idea of how we should go on. The next work should be numerical, to take some real network and test it. Second part of the work should be to include the entrance length effect, because I neglected the entrance length effect. These bifurcations have completely developed flow everywhere. Third, we have to include the transient. The pumping of the heart gives an unsteady flow, a periodic but unsteady flow. And fourth, the walls of the vessels also are known to contract and comply with the pressure of the blood. Okay? This is future work, but still, these are results which are decently acceptable. Next. Okay? Now, if the results that I derived are correct, then they can apply to natural structures, for sure, but they can also be applied to engineered structures. Why? Because suppose that you design a heat exchanger. Yesterday we were talking about micro heat exchangers for chips. They have micro channels, low Reynolds numbers, laminar flow. We can build a branch heat exchanger according to this law, which I gave you, but the function of that heat exchanger is not to supply blood, is to subtract heat. But fortunately, the law of heat diffusion and mass diffusion are the same. Fixed law of diffusion is similar to Fourier law of conduction. Okay? So the equations remain the same formally. There are different coefficients, of course. So we can apply this theory to the design, optimal design of heat exchangers, to see if we can build better designs than we can build with constructed theory. Okay? Thank you very much. Go ahead. Go ahead. And if you have questions, I'm here.
Dr. Abel has a question. Well, actually, when you were talking, I was working, same as you do.
I know, you didn't listen.
Of course I was listening.
I'm upset.
Gosh. No, actually, I just sent you the paper.
Mm-hmm.
And let me tell you the name of the paper. We just published a paper, the beginning of the year, December the 31st. Was accepted because he's one of the
co-author.
And it's called CFD Study of Constructal Microchannel Networks for Liquid Cooling of Electronic Devices. And let me tell you what we did, and I was listening to you, and so you think that I wasn't listening. And go back and put the angles. You put some angles like
these ones or
no.
This.
Yeah. That angle there, the 27 till 34, we're talking about this angle, right?
Mm-hmm. Mm-hmm.
So let me tell you a story. Years ago, Asensio no está aquí? No? Asensio is in the other. I was just like one of those old professors that are, thinking. So I was there in the going to the cafeteria. I never go to the cafeteria. It's a waste of time. So, but it had rained, and there were some leaves on the floor. So, absent-minded professors, what we do. I went back to my office. No need for the cafeteria. I started thinking, because I started looking in the leaves that I was picking, and I got 2 or 3 different ones. So at that time, Carlos and all the kids, the new professors, they were students, and Asensio was in my office. I said, look, Asensio, go and check all the different trees that there are here, and find me leads for everyone. So then he went, we didn't student, he said, because I told him. So he brought like 10. I say, you're going to go home, and then you're going to take a picture, and then put that in a program that we can start measuring those angles. And we came to an angle of 37. Okay, it was like kind of a statistical angle that we found. So then at that time, we tried to implement that via biometrics, not calling it allometric.
I remember the paper.
Right. So then he came back and he said that 30 days later, he said, it's 37 degrees. Actually, I think we made a mistake. It was 38. So anyhow, we applied that for fuel cells, and it didn't work. You see, in fuel cells, you had the hydrogen distribution, and then you are going 2D, but the hydrogen has to go 3D because it has to permeate through the membrane, right? So then it's like you were talking about the veins here and the capillaries. So it didn't work. We did the analysis. He graduated. That was for his undergraduate. And then we came with the idea that it could work to cool heat sinks. So then Carlos at the time, because that paper was 7-8 years ago, wasn't it? He was also a student. So we tried to start making like combinations of that, but for heat sinks, and it worked. So we were getting a much better heat sink by following, but it was kind of a combination. The Hess law plus what we had applied biomimetics. So, what do you think? I already sent you the
What
paper.
is the question?
Well, because I think you were saying that that's what we also believe, that yes, you do the branching, but it all depends on what you really want to do. Like, what do you want to reduce? The pressure drop or you want to get the hydrogen easily to the other side,
mhm.
or you want to cover more area. So I would say that nature is kind of a combination of all those things. So
I agree. See, what I'm saying is that the next step should be something like this. I don't want to confuse you, but these diagrams are derived on the assumption that this branch supplies this rectangle, and these two branches supply this other area. But now, this is diffusion. Okay? They supply by diffusion. So there is a high concentration of oxygen, let's say here, and it diffuses up to here. This is a cell that still needs oxygen. So we know that the concentration profile in this 2D representation is like a log profile. But then this must be the limitation. In other words, I don't think that in nature the ratio H over L is free. I think the ratio itself is dictated by the maximum distance at which the oxygen diffuses in the tissue. So maybe that A over L is related to the diffusivity of oxygen in tissue. And then if we find that, but that needs some more work, then we can close the circle, so to say, because if you diffuse, then you have a certain area. If you dissipate heat, then you have a different area. If you convect heat or radiate heat, you have a different area, because the area of service is different. That is what I'm aiming at. Okay? Other questions?
Other question?
Yep.
Thank you.
Ladies first. Yeah.
You have talked about symmetric branches. Have you ever studied asymmetric branches?
No, it's more difficult.
Because you would need it to model the network.
I know. No, I didn't do it because it's too difficult. So I will do it next time.
Thank you. Oh, thank you.
No, thank you for. No, all of these things have limitations. Okay, so I'm sure that if Bejan was here today, he would talk about the limitations of this theory. So you're right in stressing this. Yes, I only treated symmetric bifurcations. Okay, next year.
Another question?
You were talking about the river, how they adapt according to the geography, but it could happen the same in the body. I mean, it could be the all the bones, all the muscles, the first one in priority, and all the veins are the second one, and they adapt according to the geography of the body, and there could be a lot of angles depending of the structure they were passing through, no?
I understand what you're saying, but the thing is that in, let's say, for our species, okay, but we can take animals like elephants or apes or whatever. At the microscopic level, all structures look the same. So if you take your brain and my brain and take a section like the one I showed before, you couldn't tell which is mine and which is yours because they are very similar. So it's true that there may be some idiosyncratic, I don't know, I have some point in my muscle where I have, I don't know, whatever, a cyst or something. Then the flow around there would be different. But on the major part of the capillary flow would be the same. Okay?
I find this concept very interesting,
Thank you.
but I also find it difficult to grasp the idea that we can generalize their use in other type of systems. The analogy with respect to what nature does in some fields and their application in diverse fields of study it's been very useful, for example, in optimization with genetic algorithms and colony algorithms, etc. But I see here the idea of diffusion, organic tissues, etc. Very nice. And if you see the leaves, like Abel was saying, you probably will see some common factors because it's organic tissue with probably certain dimensionless groups, analogies. But I don't see why this would have success when applied to heat exchangers, for example. Would you elaborate on this?
No, I understand the question. Okay, let's suppose that these are channels in a heat exchanger. Okay? And let's suppose that the temperature of the material is constant. Okay? All of this is a T disk, T heat exchanger. Okay? 400 degrees. I don't care, whatever temperature. And I have a flow of water coming through. The heat exchange happens through the surface of the pipes. And the heat exchange, the quantity of heat that is absorbed by the pipe is given by pi r square h L. The area times the coefficient of heat transfer multiplied by the delta T. Okay? So that's the formula that allows me to compute how much heat I get out of this plate and how high is the temperature here. But of course, there will be an entropy generation which is given by delta P times Q. So the same as here. So I can divide the entropy generation, instead of dividing it by the mass flow rate, I divide it by the Q. Now the mass flow rate was proportional to the area. Can you go 2 things back? Here. The mass flow rate is proportional to, well, I didn't write it. No, I didn't write it anywhere. It's proportional to pi r square L0. The heat transfer is proportional to pi r square L0. So the formula is the same, because diffusion and heat transfer have the same equation, okay, diffusion equation. Now, if I have a different type of equation, then I would have a different MD. But the theory would still give me a different shape or a different profile of different angle, but still the reasoning would be the same. That is the power of the theory, I think. I don't know if I answered your question.
For instance, on the shell side of heat exchangers, you have other phenomena which you don't have here.
No. This is valid only for branched heat exchangers.
Okay.
Yeah. Not, no. That's clear. That's clear. I'm talking about branched heat exchangers. Or what is called porous heat exchanger. That could apply also there. Because if you think of micro bifurcations, then Bejan has already done that with his constructal theory. With micro bifurcations, you can obtain the same results as with the Darcy formula for it. Okay? Thank you. Other questions? Yes, I'm sorry, you have been neglected there.
Well, I'm interested about hemodynamics, and I want to know if you will consider the no-Newtonian fluid as a blood in the future.
Yes, I am considering it. It's a difficult thing.
Mm-hmm.
There has been one paper by a guy called Miguel. It's on my computer. If you want, I can give it to you.
Yes.
He did a numerical simulation of a realistic network using non-Newtonian formulation, and he obtained some interesting results, but the algebra is very difficult. And I think what I'm going to do is to do a numerical simulation using non-Newtonian viscosity. So I can get the results without going through the algebra, because putting the algebra of non-Newtonian here, it's difficult.
And what about coagulation factors of the blood?
No, it's not included, no. Because that would change the shape of the Poiseuille flow, and that is not included in my... what I would like to do in my numerical simulation is to allow for the compliant wall effect. That can be done. But coagulation, that's something far away in the future. Okay? Yeah. Thank you. Okay. No other questions? Can we go home?
En Irapuato no tenemos preguntas.
Finished?
I think so.
Thank you very much.
Thanks very much, Dr. Sciubba.
You want to? Wow.
Bueno, con esto terminamos las sesiones de nuestros expositores. Vamos a pasar a la sesión de cierre. Vamos a darnos unos 5 minutos para que se organice esto. ¿Sí? Gracias.